Welcome back, Quadrature fans. Today we will continue our series in geometry for quadrature, and in particular we'll talk about affine geometry. And I'm kind of new to this. I'm learning this. I'm looking at the internet. Norman Wahlberger has some series on affine geometry, and so it's going to be a little bit of shared ignorance, but bear with me. Definitely I need feedback. But affine geometry, basically, that's what we're after. So let's look at the situation like this. Okay, so we have basically, here's our little box with a diagonal through it. And the box goes from 0, a over 2a. Right? That's the run, or the base. And the height, or the rise, is 0, b over 2b, right? 0b. So the slope from Euclidean Cartesian system, where you have a right angle, that's what the Euclidean system insists on, a right angle. Okay, well, it's b over a. And in affine geometry, this is, like I said, it's going to be a little bit of shared ignorance. And there's a lot of it on my part, but in affine geometry, we can't really distinguish this scenario from the straight scenario from this scenario here. It's all the same thing to affine. At least that's the way I understand it. But let's suppose that we happen to line up and match the Euclidean system, right angles. And so Euclid tells me in the affine geometry that slope is b over a. Right? Okay. Of course, the area is always b times a. That's just the way it is. Okay, so here we are calibrated by Euclid when we're at a nice right angle, and the ME, that's the slope according to Euclid, is b over a. MA, that's slope according to affine, well, b over a. So we're calibrated, right? So let's do a little bit of a shift. We're going to shift this thing. It's a Cavalieri shift. And in affine geometry, we maintain strict parallelism this way, up and down, and we also have parallelism this way. So it's linear. Okay, so, whoa, it falls down. So let's look at this situation here. Basically what we've done was we've taken the original, here's our triangle, here's our diagonal, and we just did a Cavalieri shift of b over 2. See that? I shifted a distance b over 2 according to Euclid. Of course, affine doesn't know that he's been shifted. He can't tell. He is completely oblivious to what's happening. All he knows that he's got some markers that Euclid put on me originally when he calibrated affine. He said, okay, you're a 0, you're an A. Right? 0, A. And you're 0 and B. 0 and B. Right? And so our diagonal, which this has now become this, well, what is that? According to Euclid, it's rise over run. Well, that's b over 2 divided by a, which is 1/2 of BA, which is 1/2 of the original slope. And you can see it, it's more shallow to us. But according to Affine, he looks at this and he says, well look, I have a marking. I have 0, a over 2, a. So my run is a. And my rise, well, that's 0 and b. So it's b over a. So according to Affine, his slope is invariant. It's b over a. To Affine, slope is invariant under a Cavalieri Shift condition. Now we know that area is invariant, right? You start like this and you shift it. Has the area changed? No. So that's Cavalieri's principle, basically. And when we ever normally think about Cavalieri's principle, we normally think about area or volume, things like that. See, here's volume. The volume hasn't changed under my shift. But hardly ever do I see literature out there that says slope is invariant within this system, within this affine system. And the slope is b over a, unchanged. Okay? Well, let's go further. Let's do more shifting. Let's shift it all the way by a distance of b from Euclid's perspective, right? I've taken this. That's our original setting. And now I shift it b up. And look at my original slope. The diagonal is here. You can see that the diagonal from a Euclid's perspective, this slope, ME, is 0. It's totally flat. But from Affine, he cannot distinguish this condition from this condition from this condition. He has no clue over angles and distances. Well, he doesn't have a protractor. To him, this is 0, this is A. And to him, that's invariant. So what is the slope? Well, it's rise, which is B, to run, which is A. Look, he's got a marker. Here it says 0, here it says A. Even, you write it down over here. That hasn't changed. So he says, my slope over here is rise over run, which is B over 2, B over A. Unchanged, invariant. Slope is invariant within affine system. That's key. When I thought about it, that just hit me. And I says, yeah, that's it. Because I knew that area was invariant. That's basically Cavalieri's principle, and so I'm not going to push it much or try to prove it to you. It probably would require some sort of a limiting process. Notice how thin this is. Well, you got to make it super thin to make it continuous. But that's beyond me. So I just say, yeah, if you understand the deck of cards, sliced cheese, sliced bread, you understand Cavalieri's principle. And so I use a deck of cards, and that's kind of nice. So let's investigate further. Let's investigate the scenario of y equals x plus x. Right? You've seen that before. Well, if you do the algebra, well, that's y equals 2x. Right? And so immediately you say, well, the slope of this thing is 2. And here you can see the slope is 1 and the slope is 1. So each of these contributes a slope of 1, right? These functions, they contribute equally. And the plot of this system within the Euclidean Cartesian framework, which insists on a right angle right here, right? Well, it's this. This is the plot of x plus x. There's your x plus x. It's a shape that looks like this. It doesn't look like this. How do you get from this to this in a Euclidean system? Not easy. Now you can flip it around and effectively you get a squared. That's the equivalent area, right? A squared. This one, 1/2 base times height. So it's 1/2 2a times a. Again, that's going to be a squared. So the equivalent area is a squared. That's fine. But how do you get from here to here? And the answer is you need affine geometry. Because with affine, which is kind of the geometry of the Cavalieri Shift, basically start out, see this box here? And here we have our triangle, right? Simply do a Cavalieri Shift. And so, whoops. So what happens? Our box shifts like this. And so here's our plot. This is our contribution. So look at the slope contribution of this one. It's rise, which is a over a. His slope contribution is 1. But notice that this will nicely stack on top of this. You see that? In the affine system, we can do a Cavalieri shift on this, shift it down to here, and now that matches. See how it matches? These two areas are the same, and so I won't belabor the area is pretty easy. Yeah, it's already a squared, right? We already talked about that, but I want to look at what about the slope? Look, in the algebra, the slope contribution is 1. Here's another 1. Each of them contributes equally. And how does that relate to geometry? Because, you know, in a Euclidean system, it doesn't quite work out. At least I find that if I switch over to what I think is called the affine system, there basically you get the slope contribution, and that's rise, which is a over a. And that's 1. So, you know, his contribution is still 1. And his contribution is 1. So, together, they contribute to 2. So, anyways, that's kind of the beginning of my series. And we'll be talking about affine and even crazier geometries than that, which that'll be in our next installment. But for now, just digest this concept and again, get yourself a deck of cards and do some Cavalieri shifts and let it soak in. And I think that you'll begin to understand that area is invariant under a Cavalieri shift, and equally slope is invariant within the affine geometry under a Cavalieri shift. So, thank you. What's our motto? Before there was calculus,
there was quadrature.
You got it. it.